Good evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course. This course is being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. Okay, and it's a 12-week course, and we are into the third week of this course. And related to this third week, we are conducting this live tutorial session. The theme of this week's content is quasi-one-dimensional isentropic flow. Instructor for the course is Professor Niranjan Sahu from, again, Mechanical Engineering Department, IIT Guwahati, and I am a research scholar here. So we shall wait for another couple of minutes. After that, we'll start with today's session. Thank you. Okay, so I believe we can start with today's session. So this is quasi one-dimensional isentropic flow. So we have seen one-dimensional isentropic flow in previous lectures, but then here we will be discussing quasi one-dimensional isentropic flow. Why quasi one-dimensional? So flow will be in one direction only, but what we will be doing is we will be changing the area along the flow. The cross-sectional area will be changing in which the flow is taking place. So that is, sorry. So that is why we are calling it quasi one-dimensional isentropic flow. All right. So three lectures are there in this week's content. Lecture 7 to lecture number 9. So lecture number 7 to lecture number 9, three lectures are there, right? So we will take these lectures one by one. Okay, the topics and questions related to each lecture. So let's start with lecture number 7. So its topics. So first topic is effects of area change on flow properties. So if the area of the cross section changes, okay. So if a flow is happening and the area changes, okay. So this area, this is A1, this is A2. So what happens then? Okay. Expansion process on Mollier diagram, expansion process on compression process on Mollier diagram. Adiabatic flow with friction, adiabatic flow with friction, diffuser action, and nozzle action. So lecture number 7, if you see. Now, using Mollier diagram, expansion process, if you see, Mollier diagram basically is HS diagram. Okay. Because we are talking about isentropic flow, right? The entropy will remain same, right? So from 1 to 2, let's say the flow is moving from one state to second state, right? Let's say it is moving in a duct. From 1 to 2, it is moving. Let's say what type of flow it is, I'll just not mention here. Okay. Now it is expanding, so its enthalpy will decrease, right? Right. And this change in enthalpy, decrease in enthalpy is being converted into its velocity. Okay. So, or maybe, if I call it not, or all right, I can just write it. So it is something like this. Okay, the total is changing to, so your flow is expanding. So some part will convert into your velocity and then some static part will remain, right? Then, and the direction will be downwards, right? In your compression process, what will happen? The direction will be upwards. Okay. Here your enthalpy is going to increase, right? So this is expansion and compression using your Mollier diagram. Then comes the concept of governing equations. Okay. So what are the three governing equations? First is your continuity equation. So it is like this. It's a differential equation. This is your continuity equation. Then your momentum equation. Okay. Your momentum equation is this. So this is your momentum equation. Okay. Or like this. Then your energy equation. It is like this. Like this. Okay. Or you can write it this way. So this is your conservation equations or governing equations for quasi one-dimensional isentropic flow. Okay. Right. Then moving on to questions. Then we have first question here, which says that what is the maximum speed that can be achieved by accelerating stagnant air at standard sea level? So what we will be doing here is, yes, Based on the enthalpy data, we will, sorry, based on the enthalpy data, we will try to uh, get this maximum speed, because eventually this enthalpy is holding all the potential, okay, of accelerating the air, right? So question one solution. So R is given as 287 in SI units. Okay. So P naught is given as this. Okay. And T naught is given as 288 Kelvin. Okay. Then using energy equation, it's something like this, right? So this we can write as this way. Okay. Now here, this U has been asked in the question. So that is the whole purpose of using this energy equation. Okay. Now, because whole of this potential is being consumed, so we will suppose that at the end, the temperature will be zero, right? Hypothetical, 0 Kelvin. So this will be CPT naught 0 plus U square by 2 implies U equals to 2 into CPT naught by 2. Sorry. This. Now CP we can write as gamma by gamma minus 1 R, and T naught will remain as it is. This. Now placing values, because this is air, so gamma will be 1.4, right? So R will be 287 into 288. Now solving this, please calculate this. What will this come out to be? I'll also calculate. I'm getting this 760.85 meter per second. for this question. So I have just solved this question. What is the maximum speed that can be achieved by accelerating stagnant air at standard sea levels? So I just use energy equation here. Okay. Enthalpies I have equated first. Then I have split this Cp into gamma by gamma minus 1 into R. And this way I have solved this question. So this is question number 1. Then next question. Yes. So doubts are regarding path which week's content. You can unmute yourself.
So it's week 2 and week 3.
Wait. Yes, now speak.
Yes, it's week 2 and week 3.
Okay, week 2 and week 3. So how many doubts you have?
Uh, I
In
have,
3, 4. Yes,
yeah, I have 3 doubts.
3 doubts. Okay. So maybe. So I'll tell you all right. So from week 2 and week 3.
Yes.
Yes. Okay. So in between, if you have some doubt on what I'm just discussing, you can let me know. But we'll take your doubts also. Let's see.
Okay, sir.
Maybe after one hour, right? Maybe at 7, right? When we take break uh, around that time, maybe first
Okay,
break
sir.
that we take.
Okay, sir.
All right, then you can mute yourself. Then second question we have a gas with reservoir pressure of 20 bar exits a D level nozzle at 2 bar. Calculate the exit Mach number assuming the specific heat ratio is this. So what is given to us? Reservoir pressure is given as this. Okay. Exit pressure is given as this. Then gamma we have been asked to assume as this. And exit Mach number we have been asked to calculate. Right. The question number. E naught is 20 bar. E exit is 2 bar. Then Mach exit we don't know. And gamma is 1.47. This has been asked. Now what do we do? Exit Mach has been asked. What should we do? So we will invoke isentropic relations, okay? One of the isentropic relations. So this is like this. P naught by P is equal to ooh, P naught by T is equal to 1 plus gamma minus 1 by 2 m square. Okay, like this. But here then T naught by T is not given. Pressures we have been given here. So what I'll do is because T naught by T, because P naught by P is T naught by T, gamma by gamma minus 1. Okay. So now I can write this as gamma minus 1 by gamma. Okay, T naught by T. So this I can do. Okay. And because here exit pressure, static exit pressure has been given. So this I can do this way. Okay. Any doubt? Just ask me in this numerical. Okay. So then now what we can do is we can use this in here. Okay, we can use this here. P naught by PE. This we can do, right? Now we can place the values 20 by 2, 1.47 minus 1 by 1.47 equals to 1 plus 1.47 minus 1 by 2. This we don't have. Okay, so this becomes 10 raised to power 0.47 divided by 1.47. Oof. This becomes this. Then minus 1 also. Okay, from here, I'm taking this here. ME square. Okay. So now please solve this. Take your calculators out. Try to work this out. Yes. What are you getting? Okay, so I have this as the answer this question. You can just check by yourself if the calculation is correct. Okay, then we will move on to next question. You do for the exam, you don't need to memorize anything. If it is uh, mostly tables will be given. Okay, so gas tables you are talking about. So if somebody has asked about the gas tables, so they will give you these tables. You don't have to memorize. It's not possible, right, to memorize these big tables. But isentropic relations, these basic things you should know. But formulae you should know, right? So that at points there are even formulae given in the question where the formula is not too commonly used. Okay, but otherwise formula you'll have to, I believe, memorize. But tables you need not to. Yes, gas tables we need not to memorize. All right. So then next question we have. In the previous question, if the reservoir temperature is 3000 Kelvin, then calculate the exit velocity. T naught is given as 3000 Kelvin. U exit you need to find out. R is given as 287 joule per kg Kelvin. So this has been given to you. Same using isentropic relations, this can be done. So please try to do this. So again, I'll use this relation. T naught is given as 3000. P exit okay. Now from previous question, we will use Mach here as 2.149. Okay. So only one unknown is left then. This is there. Okay. Now work this out. What will it be? Just calculate. This is 1 plus 1.085. So this becomes, I hope you are calculating by yourself also with me. So this becomes this. Now if you calculate this, what you will be getting is 1438.71 Kelvin. Okay. So for velocity, what we needed is, because so that is the reason why we are calculating this TE. Okay. Exit temperature, static exit temperature. So from here we can get the velocity. So 2.149. Okay. 1.47 into 287 into, now if we calculate this, this will come out to be 1674.25 meters per second. So this is your exit velocity if your stagnation temperature, reservoir temperature is 3000 Kelvin. I hope this is clear. We have used Mach number from previous question, this question, where pressures were given. Okay. So from here, first we calculated Mach number, and this Mach number we have used here to get the static exit temperature. I hope this is clear. Then next question is, This question is from one of your slides. So a steady one-dimensional flow in the absence of dash and dash is called as isentropic flow. Any answer? The answer to this question is A. A option. Heat transfer and body forces. And I hope you remember uh, what body forces are. So gravity, magnetism, okay, so by virtue of its body is what we call as body forces. Then next question we have, in a diffuser action, what should be minimum? So there is nozzle action, and there is diffuser action. These two things are there. So nozzle action is related to increase in the velocity of the flow, and diffuser action is related to decrease in the velocity of the flow. Okay, so these are two types of basic actions. Now here it asks that in diffuser action, what should be minimum? This question basically is from that perspective that in real case scenarios, when we are using some diffuser to decelerate some flow, what is it that we keep in mind while designing that diffuser? Okay. So the answer to this question is pressure loss, okay, total pressure loss. The total pressure that we have in hand. So we don't want in any case that we lose that pressure. Okay. Pressure losses can take place because of number of reasons. Okay. Friction is one reason because of which pressure losses take place. Okay. So like I work on shock tube, so if the tube has lot of friction, in that case, the Mac I'm while experiments, the Mac I'll get is its speed will be uh, less than the theoretical speed. Okay, so it is from that perspective. Okay, question number 5, diffuser action. Then next question is, yes, next question, please try to answer this. So the question here says that in case of a nozzle action, which event must happen in the flow direction? First option is velocity of the flow increases while the pressure decreases. Velocity of the flow decreases while pressure increases. Both velocity and pressure increase. Both velocity and pressure decrease. So because it is nozzle action, it means velocity will increase. So A and C option says that velocity will increase. But about pressure, what happens? So this pressure energy is the one that is being converted into this kinetic energy, right? So if your velocity is increasing, your pressure will go down, right? If your pressure is increasing, your velocity will go down. And if your pressure is going down, we call it expansion. If your pressure is increasing, we call it compression. Okay. So if your pressure decreases, this is expansion also. Okay. And to this question is the correct answer. Then moving on to next question. Please read this question and try to answer. Okay, flow is steady, isentropic, one-dimensional, constant area duct. Not even quasi one-dimensional, constant area duct. So what will happen? Nothing is going to change. Okay, these all are going to remain same. Question number 7. Then before moving on to lecture number 8, Parth, you can ask your doubts. Hello, Parth, you're still there.
Yes, sir. Yeah, I was opening the pictures.
Yes, fast, fast.
Yes, sir. I sent a picture for isentropic flow stagnation conditions graph. Uh, in the graph in the graph uh, for
Yes, yes. Go on, go on.
yeah yeah in the second graph he marked the graphs itself at T naught and T. Should there
Hmm.
not be P naught and T?
Oh, right. Okay, all right, all right. Hmm.
It,
Right.
it should it should be P naught and P, right? Yeah, okay. And
Yeah,
I was
yeah, yeah.
having confusion on that.
Yeah, 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 because
And
right, right. That is yes, that is you're right. So there is mistake,
right,
right? Because this is the same graph only, right? Because CP into T, right?
yeah.
Yeah.
Uh, then just a minute. Yeah. Uh, so then for the formula for characteristic speed in terms of A naught, by derivation, I got the A naught to be coming out of the root. But in Sir's derivation, I think somewhere he missed the square something, the A naught is inside the root.
So this is wait, energy equation you are
But,
giving. Hmm.
yeah,
So
in that,
so this
I
is
did
from
the same derivation.
week 2, right?
Yes, sir, I did the same.
Hmm. So you are following some reference also?
No, sir. Like whenever he starts a derivation, I stop the video and then I do it by myself. And
No, that is
then
fine. No,
I
no, 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 no. That is fine. I'm just asking that did you just cross check it with some reference?
no, sir, no, sir. I haven't checked it. But then I think he missed a square
That
term
it
somewhere.
could be, it could be the case. This is which lecture number?
Uh, so lecture 5,
Lecture number 5 and slide number.
slide number, slide number 12.
Okay, I'll check this. Okay,
Okay, sir. Uh, then
and then
then, sir, from week 3, he solved a question. I have a doubt in that.
hmm.
Uh, week 3, he solved a question, and the question was to find the mass flow rate.
I have
And
yes, I'll be doing this question.
yeah, he gave the unit in kg minute. Shouldn't it be kg second? Kg per
No, he has
second.
just converted it
Oh, okay,
by
okay,
multiplying with 60.
okay.
Hmm.
Because he wrote direct, so I thought the direct answer would give us in kg per minute. Okay.
No, no, no. It's just that I have also seen. Just he has multiplied the Answer that is in SI by 60. Just that.
Okay, good. Uh,
Just that. Anything else?
so just a minute. Yes, sir. That's it, sir. That's it.
Okay, great. Then let's take a short break of 5 to 10 minutes. Then we'll continue with the session. Thank you. Okay, so we can continue with the session. So lecture number 8 in that case, quasi-one-dimensional isentropic flow part 2. So here area velocity Mach number relation has been introduced to us, and this is a very important relation as far as this whole topic of quasi one-dimensional flows is concerned. So this relation is there. Then supersonic nozzle and supersonic diffuser. So these topics have been discussed. So lecture number 8, if you see, area velocity Mach number relation. So sorry. So this relation is like this. Okay. Now, what is the meaning of this relation? So I'll just show you. So let's say we'll take ducts. Okay. Flow is happening this way, like this. And this is divergent duct, right? A2 is greater than A1, right? So what is dA in this case? Change in area is positive, right? Because area is increasing. Final minus initial. Okay. So your area is change in area is positive. Now let's see this relation. Now dA is positive. It means RHS, sorry, left hand side will be positive, right? Now, if your flow is subsonic, okay, in that case, your m square minus 1 will be negative, okay, because m square will be less than 1, right? So this m square minus 1 whole will be negative, right? Now, left hand side is positive. So to make the right hand side positive, your du will have to be also negative. Okay, so negative and negative multiplied, it will become positive. So what this implies, your velocity decreases. Okay, so if your flow is subsonic, duct is divergent, your velocity will decrease. Okay, now again I'll write this positive for supersonic. Okay, now if your Mach is greater than 1, your m square minus 1 will be positive. Now your change in velocity will be positive, right? Because left hand side is positive, so du will also be positive. Du is positive, it means final will be higher than initial. Final will be higher, it means your velocity increases. So if your duct is divergent and your flow is supersonic, in that case, your velocity is going to increase. Okay. So this is about your divergent duct. And if your duct is convergent, okay, your A2 is less than A1. In that case, things will be opposite, right? So dA is negative here. Your final area is less than your initial area. Okay. So your left hand side will be negative, right? I hope this can be worked out, right? So I'll not just discuss this. So it will be opposite to these two cases, right? So then concept of supersonic nozzle. So this supersonic nozzle, it is D-level nozzle has been discussed. Okay. So D-level or CD nozzle. What is CD? Convergent, divergent. So same logic will apply here also, right? So this is divergent, this is convergent, one divergent we have taken together and we call it D-level nozzle. So what it does, your subsonic flow is there, it will make it supersonic. Okay, supersonic diffuser. Your flow is supersonic, it is going to make it subsonic. Okay, so this is your supersonic diffuser. So this is lecture number 8. Then questions are there. First question is in a supersonic flow, the decrease in flow velocity is associated with dash in area. Flow is supersonic. Flow is supersonic means this will be positive. Okay. The decrease in flow velocity means this is this thing is negative. Okay. So positive, negative, negative. Okay. So dA has to be negative, which means your your area is going to decrease. I hope this is clear. B is the correct option. What will be the answer to this question? 0. Okay. Question number 9. Question number 10, please try to answer. Flow is subsonic, m is less than 1. What will happen? Or dA positive, dA is positive, this is negative. So this is also going to be negative. Your velocity will decrease, so your Mach number will decrease, and your enthalpy will increase. Okay. So both A and C. This is the right answer to this question. Question number 10. Choked mass flow rate, gas property table for isentropic flow. These two topics have been discussed. Also, area Mach number relation has also been discussed. So, area Mach number relation, if we talk about, then it is this. Now, what is this relation? This relation basically says that if you have a duct, the minimum area is your throat. Okay. Then you take whatever area that comes in your mind, right? Some cross section, whatever you take in this tube, what will happen? Your area and Mach number. So let's say I'm taking this place. It has area A, it has Mach M. So how they are going to be related? So this is the relation. A star is the minimum area, right? Minimum area or throat, you say. Okay. choked mass flow rate? So what is choked mass flow rate? So you have this duct, okay, or nozzle, CD nozzle. Flow is taking place like this. This is your throat. So let's say it enters subsonic. So what will happen is, because first you have convergent section, the flow will accelerate. Okay. So at throat, the maximum velocity that the flow can achieve is your Mach equals to 1. Beyond this Mach does not go. Okay. Now beyond this Mach, the flow doesn't accelerate at the throat. Okay. And this condition defines the mass flow rate in a CD nozzle or in a nozzle. Okay. So the mass flow rate related to this choked condition, this Mach 1 at the throat, is basically your choked mass flow rate. I hope this is clear. Okay. Then expression for it has been given. M star has been given like this. Rho AV. Okay. This is there. This is also there. So this is for your choked mass flow rate. Then we'll move on to questions. So in a CD duct, choked flow condition is there. So now it says that your density will decrease. Okay. With respect to whatever it was there in air. Right. So the percentage decrease, then it asks. So this ratio is from previous week's content. Okay, like this. For air, we can directly give it, right? You should remember for air, you should remember. So it is this. So then percentage decrease. So this comes out to be 36.6%. So this is your question number 11. Then let's see next question. Oh, so this has not come out correctly. So it is basically this. Okay. So a storage chamber is maintained at 5 bar and 20 degree centigrade. It supplies high pressure air to a device. The air is found to be leaking through a small hole of 5 mm diameter. Calculate the mass flow rate of air leaking through this hole. So this is from your lectures only. Okay. So initial pressure is given as 5 bar. Temperature has been given as 20 degrees Celsius. Okay. So this should suffice, I believe. So your mass flow rate is 0.68 by RT naught into P naught area. So this is 0.68 divided by 287 into, so this is 273 plus 20 equals to 293. So this is 293 root P naught is 5 bars, the 101325. Actually, 1 atmosphere is 101325. let's say it is this. Then area is area of circle. Okay. Pi d square by 4. Now if you calculate this, and multiply by 60, this will come out to be 1.4 kg per minute. Okay. This is question number 12. Then question number 13. An airplane model is tested in a supersonic wind tunnel. At a point on the model, the pressure, temperature, and flow Mach number have been given as these. Calculate the stagnation pressure, temperature, characteristic pressure and temperature, and flow velocity at that point. So pressure has been given as 0.9 bar, temperature this, Mach is given as 1.5. Now stagnation pressure temperature has been asked. So this is from the table. From the table this and T naught by T is equal to 1.45. Implies P naught equals to 3.67 into 0.9. So this will come out to be 3.3 bar. And T naught is equal to 1.45 into 250. So this will come out to be 362.5 Kelvin. Okay. Now characteristic pressure and temperature we need to find out. So characteristic means choked condition or at the throat. Characteristic. So we'll multiply and divide by P naught. Then again multiply and divide by P. So P star by P naught for gamma is equal to 1.4 is 0.528 and P naught by P is given as 3.67. Okay. And P is given as 0.9 and if you work this out, this will come out to be 1.74 bar. Again, characteristic temperature by T naught to T naught by T into T. So this is 0.833 for gamma equals to 1.4. And this is from table 1.45 and T is 250. So this will come out to be. Now talking about velocity. Velocity Mach into this. So Mach is given as 1.5 and gamma this A is gamma RT. So this is 1.5 into 1.4 into 287 into 250. So if you calculate this, this will approximately come out to be. So this is for your question number 13. Okay. Then question number 14 is there, which asks that in a D-level nozzle, the maximum mass flow rate is reached when the Mach number at the throat is, four options have been given, 0.3, 1, 5, 10. So when Mach is 1. So we have discussed this. Okay, so this is there. So B is the correct option. Then next is the area Mach number relation is dash in nature. So what is the nature of this area Mach number relation? Area Mach number relation. This. What is its nature? So this relation is quadratic in nature. Okay. So out of the four options, B is the right answer. Okay. So this is it for today's session. I'll just conclude in that case today's session. So quasi one-dimensional isentropic flow. Three lectures were there, lecture 7, lecture 8, lecture 9. In lecture number 7, we started with now what is nozzle action, what is diffuser action. Then we saw governing equations for it. Okay. Then in lecture number 8, we saw area velocity Mach number relation, a very important relation. So how the nozzle action, how the diffuser action takes place, or how the expansion and or compression takes place. So this has been discussed here. All right. Then in the last lecture, so choked flow has been discussed. Okay, in a CD nozzle, when your Mach is 1, so that condition basically is called as choked condition. So this is it about, and then there are inferences related to area velocity Mach number relation. I believe that has been discussed. So this is it about today's session and week number 3. Next session again will be on coming Tuesday from 6 to 8 p.m. Till then, I take leave, right? And in between, maybe one session I'll try to prepone. So that I'll let you guys know. So that will be the one on 10th March. That mm, uh, I'm planning to prepone it. So let's see. Okay, till then, goodbye. Thank you. Thanks for watching.